OI, soft dedupe, an efficient data reweighting method for speeding up language model pre-training. Cool paper today. Very, very simple method. No real add-on in terms of computation, but I think they said like 25% faster to train the actual model to the same level, or you can just train it to better performance. The idea here being that we should be more intelligent with how we use our data, with which data we weight more or less heavily rather than just weighing it all evenly throughout training, right? Before we get started, like, subscribe, comment, all the YouTube things, join the Discord to discuss, follow on Twitter and LinkedIn. And if you're a big supporter, you can hit that YouTube join button down below. It's as low as $1 a month to help me out. And it also gets you early access to my videos before they go public. But yeah, let's get to it. So when these LLMs go to read the entire internet worth of data, right, there's obviously lots of duplication throughout that data, and redundancy beyond a certain level impairs the performance. What you end up seeing is if people copy the same New York Times article across the internet many times, the model, as we know, memorizes that data. And key here is memorization isn't just bad in terms of copyright, it's also probably bad in terms of learning. Reason being, the hope is anyway that when data gets shown once, maybe twice throughout the entire training period, and it's all brand new data, we're hoping that the models can actually glean some semantic patterns off of that, some meaning. Whereas the moment you start giving it the same piece of data many times, its incentive is no longer anymore to just learn the semantics off of being glimpsing the data. It is now really incentivized to memorize, right? And most current deduplication strategies of said data are hard deduplication, meaning that they actually fully remove documents from the training data. This is totally necessary. We don't want just straight up duplicates. It can debatably go a bit overboard if we're deduplicating based off of just certain engrams being repeated. You might have a otherwise good Reddit post contain a single sentence that is plagiarized, in which case maybe you do want to actually still include that data. But if anything, my impression, anyways, is that on average, even these hard methods still are a bit insensitive and could go further. Now, this paper is going to be introducing the concept of data commonness, a metric that quantifies the degree of duplication by measuring the occurrence of probabilities of samples using an n-gram model, an actual separate model from the primary LLM. And what they're going to be doing here is taking any samples that have high commonness, aka high probability given the n-gram model, and assigning them a lower sampling weight. Now, here's the kicker. The actual results show that these models could achieve the same performance as the baseline with 26% fewer training steps, meaning keep training at same amount, you get even better performance. And this is happening even after applying this method to already rigorously deduplicated data sets. Now, what this looks like is out in front of our normal cross entropy loss function, right? We add these sampling weights, Wx, which themselves are inversely related to those probabilities that we already mentioned, which were derived from said n-gram model, pre-trained unigram model, right? So what it's doing here is saying if even the simple model gives this token a high chance of occurring, then take 1 divided by that chance, which is not a very large number. Let's say a 1 divided by 0.9, that's like 1.1 or something, and multiply that by a regular loss. Whereas if the simple model gives a very low chance of that token occurring, maybe a 0.1 chance, then 1 divided by 0.1, now suddenly you have a 10 here for your weight, and that's a much larger number. It blows up and makes larger the actual loss we get on that token. And as I said, we derive those chances from a simple n-gram model, which we trained beforehand, which is an extra step in all this computation, but those models are pretty simple and small. They tested all this out on multiple different data sets, key being here that some data sets had more or less hard deduplication already happen to them. And as we said earlier, this approach did consistently outperform the baseline for average perplexity across all data sets, not just the non-deduplicated one, also the hard deduplications still had big results there. Here we see perplexity curves of the baseline model versus the model that got to use the soft dedupe loss on both the pile test set, aka lots of duplicates in here, versus slim pajama, which should have fewer duplicates inside of it. And you see by the orange line being lower down, we do in fact get lower perplexity. Here, a bunch of downstream benchmarks, as you would expect, all pretty common ones. And there were two in which the hard dedupe method did actually perform better, and those look more like memorization based data sets, trivia, Q&A, and web questions. So if anything, don't get me wrong, lower benchmark is still lower benchmark, but of any benchmark to actually get lower in, these seem like pretty good ones. Looks to me like less memorization, the fewer actual hard facts we can force and code into the model, the better, in my opinion. And to quantify this actual improvement, we can get the same performance as the baseline, as the no dedupe in Perplexity, with 26 to 39% fewer training steps. That is wild. That is huge cost savings right there. Now, in reality, are you actually going to train the model less? No, you're going to train it the same amount still, and you're going to, instead of taking the cost savings, take that better performance instead, but still. Now, the only real question of this method is the actual computational cost of this reweighting. Now, using the n-gram model during the primary model's training is really not a huge difference, pretty negligible, but you do have to train the n-gram model ahead of time. And how tough is that? Not tough at all. It's just an n-gram model. They literally did it on a CPU, it seems, for 40 billion tokens with a n-gram model of 4 being the n. It only took 4 CPU cores, 5 hours of training to actually train the model, and then to get those commonness numbers, which I guess they actually could do ahead of time as well. It took said 4 CPU cores just 2 hours. So really, yeah, negligible. Do this on your home computer before you ever even hook into Lambda Labs or anything. My conclusion today is that this is a cool idea, but probably not the end all be all, as in terms of how to implement said idea. They did mention some alternatives, such as focal loss, which is a 2018 loss function. All it does is add a term in front of cross entropy loss, which weights the loss curve more heavily towards uncertain tokens and really lets the model care less about certain tokens. So even without any extra training or anything, literally just a very, very simple, I believe it's something minus something to the power of 2 right in front of the CE loss. Very, very almost no additional calculations. That focal loss actually ends up with similar results of getting the model to memorize less and focus more on uncertain tokens. And honestly, you could even try combining them, but the point more so being there are probably other methods with which to do this. Personally, the one I was thinking of is, can we use somehow the model's own perplexity metric, the model's own sense of surprisal, to calculate this W, the actual degree to which we should weight these loss values. That I think would be pretty simple, and I would love to see it. But yeah, point being, we have a long way to go in terms of being intelligent as to how we actually use our data. Hope you all enjoyed all that. Like, subscribe, comment, all the YouTube things. Join the Discord to discuss. Follow on Twitter and LinkedIn. If you are a big fan and want to support me financially, you can do so with that YouTube join button down below or my Patreon. If you do so on YouTube, you get early access to my videos. And yeah, end of video.